You have fallen into Event Horizon with John Michael Godier. John is joined today by Dr. Harsh Mathur and Professor Kate Brown. Dr. Mathur is a theoretical physicist whose research spans condensed matter physics, astrophysics, and interdisciplinary science. He did his doctoral work at Yale University and was a postdoctoral fellow at Bell Labs before joining the faculty of Case Western Reserve University, where he is currently a professor of physics and an associate dean of the College of Arts and Sciences. He was a Sloan Research Fellow and a recipient of the Dykhoff Prize for Distinguished Graduate Teaching at Case Western Reserve University and is a Fellow of the American Physical Society. His current interest is in testing the law of gravity in the outer solar system. Professor Brown is a theoretical physicist whose main interests are within cosmology and fundamental quantum mechanics, while also working on interdisciplinary projects by teaching a class on physics and art. In the last few years, Professor Brown has worked with Hamilton students on several cosmology projects. They recently showed that the symatron scalar field also obeys an electrostatic analogy and offers several interesting contrasts from Newtonian gravity.
Doctors Harsh Mathur and Kate Brown, welcome to the program.
Yeah, good to be here.
Thank you. Thank you for having us.
Now, doctors, you work in an interesting area, actually a number of interesting areas, but in this particular instance, MOND, Modified Newtonian Dynamics, as a potential alternative to things like, I suppose, dark matter and those sorts of questions but really gravity at a distance. And maybe our ideas on that might not be quite right. In this case, though, you're suggesting maybe we can look at the solar system and answer these questions and either knock MOND out or find some evidence for it, either way. This involves Planet 9, the juxtaposition of some very unusual orbits of objects in the outer solar system. How does MOND relate to that?
Yeah. So I guess one thing that I hope will answer this question and also was part of our original motivation for the project is the realization that there is a characteristic length scale or distance scale at which one would expect MOND effects to become noticeable. If you tell me the amount of mass, then I can tell you the distance from that mass at which we would expect MOND to become significantly different from Newtonian gravity. And so if you plug in the mass of the sun, ignoring all the other elements of the solar system, just keeping the mass of the sun, if you give me the mass of the sun, I can tell you the distance from the sun where you would start to expect to see effects from MOND. And that distance is about 7,000 astronomical units. So this is like the average Earth-Sun distance is 93 million miles. A lot of people know that. And that's defined as essentially one astronomical unit. So 7,000 times that is way out in the, far reaches of the Kuiper Belt region. Oort cloud, I guess inner Oort cloud, depending on where you draw the boundary. But that's relatively close to the sun. And that is surprising because I think many people think of MOND as a galactic scale phenomena or predicting galactic scale phenomena. And 7,000 astronomical units, while it's quite far from the sun, is not galactic scale. So that, I think, is one of the reasons that we started looking more closely at what MOND should be saying about the outer solar system was because there was this characteristic length scale indicating that we should start seeing effects there.
That's interesting. Now, could either of you give me an overview on the difference between MOND and what we see as the standard sort of, I guess, dark matter cosmology, for lack of a better term?
Sure, I'll take this one. All of this really goes back to galaxy rotation and the observations by Vera Rubin and others in the 1970s, where they were looking at stars, rotating in disk galaxies. And if it's a star that's very far outside the galaxy, it's really like the solar system. The further out a planet is, the slower it moves. But what Rubin and others saw is that when you look at these distant stars, they're all moving at the same speed. So it's called a rotation curve, where you plot the speed of the star against the distance and they just flatten out. And this was a big mystery. So the one way to explain it is to say that maybe there's a lot of other stuff in the galaxy that we can't see. And it turns out you have to assume there's something like 5 times as much of this invisible stuff of an unknown nature that's causing the rotation curve to flatten out. And that's the dark matter hypothesis. If it was only for galaxies, it might seem a little bit far-fetched. But then this idea of dark matter can be applied in cosmology as well, on cosmological scales. And it actually does a really good job of accounting for how the universe may have evolved from the cosmic microwave background to the present clumpy galactic structures that we see. So dark matter works on galaxy scales, it works on cosmological scales, which are much bigger. It's also motivated by particle physics, where there's a number of ideas people have about what this dark matter could be made of. Because it needs to have some very peculiar properties. It should produce gravity, but it should pass right through us, otherwise we'd see it. It shouldn't reflect light, otherwise we'd see it, and so forth. So this mysterious stuff, I mean, particle physicists have ideas about it. It works in cosmological scales. It's a very attractive idea, and it's the dominant paradigm. I think the one weakness of this is that people have been looking for it for about 40 years and not finding it. Including, we had a group right here, which was one of the leading groups in this business. So we used to follow it quite closely, and that was the summary of all their talks: no signal. So that's the one reason why I think it's worth thinking about alternatives. And alternatives are, the most interesting alternative is MOND, which is a modification of gravity. And as Kate explained, on galactic scales, what MOND says is that, or on any scale really, what it says is when gravitational fields become weak enough, then Newton's laws don't apply. Something different, which is explicitly described in MOND, kicks in. So if you go to the rim of the galaxy, where gravitational fields are weak, you get MOND gravity, and MOND gravity is designed to explain the flat rotation curves. So that's the original context for MOND.
Can I add to that?
Absolutely.
So I guess there's the machinery of MOND and the equations and kind of the global view that it is a different law of gravity. And that's true. I don't dispute that or disagree with that or really have anything to add. But there's another element that I guess I wanted to mention of how people might think of MOND. And it has to do with, I guess, viewing the core idea of MOND as not something that relates to galaxy rotation curves or even galactic scale phenomena necessarily, but the core idea can be understood as proposing a fundamental acceleration scale. And this is kind of like there being a fundamental speed in the universe, which is the speed of light. And when you're much below the speed of light, traveling at speeds much less than the speed of light, then you can ignore all relativistic effects. And Newtonian physics, classical physics is perfectly good at describing things that are much lower than the speed of light, speeds much lower than the speed of light. Yet, if you approach the speed of light, then you need to make some modifications to the laws that govern motion. And Einstein provided those modifications. And so far, they've all been, many of them have been observed or upheld. And there's a similar thing that is predicted by MOND. If you take the idea that MOND is fundamentally about a new acceleration scale, an acceleration scale that would be essentially a new constant of the universe along the lines of c, the speed of light, this new acceleration scale would be somewhere around 10 to the minus 10 meters per second squared, which is very small by earthly standards. For example, the acceleration near the surface of the Earth is about 10 meters per second squared, which is 10 or 11 orders of magnitude greater than this proposed fundamental acceleration scale that MOND has. But conceptually, I think it's helpful to think of MOND as the core idea being that there is a fundamental acceleration scale that the universe has. And when you are at accelerations that are much greater than this acceleration scale, you can completely ignore the corrections that MOND would offer to Newtonian gravity. But when you are close to that acceleration scale, that's when you need to bring in or account for the modifications that MOND proposes. And so in that way, I think it's kind of conceptually similar to like special relativity and the speed of light.
I can see the attractivity of that. Now, does MOND, basically the standard way that we view it, does it actually completely eliminate dark matter, or is some measure of dark matter still required?
Yeah, I guess I had watched your video as well, and I'm not aware of any MOND models in which there is any dark matter, but I guess I could be wrong. I mean, there are things that play analogous roles to dark matter, and I'm just going to stop here because I defer to maybe Harsh knows about some varieties in which there is a little bit of dark matter, but I guess I don't know of any.
Yeah, so I can chime in there. Cosmologists, they're a hardworking group of people, so almost everything under the sun has been tried. The thing is that MOND works really well with galaxy rotation, and dark matter has trouble producing some of those observations. But conversely, MOND really doesn't work beyond galactic scales. If you try to apply it on cluster scales, it has a lot of problems. So people have always tried to see if there's some way to combine the strengths of both. And I think a clean solution would really be that somebody should figure out. The reason you can't apply MOND on large scales is that it's a non-relativistic theory that only applies when things are moving slowly. And we don't know the full MOND, the fully relativistic version yet. So, I mean, I think a purist approach would be, can we just explain everything with MOND, including cluster scales? And there are people trying to do that, cluster and cosmological scales. Or can we just explain everything with dark matter? But there are other approaches where people are saying, well, maybe we could have a bit of both, where MOND is taking care of some of the details in galaxies. So there are some models like that too. There's one very concrete set of models I'd like to flag, which is these ideas developed by Justin Curry at University of at UPenn.
So yeah, it's difficult to tell when you don't have a complete picture of something, and you have to come up with a hypothesis. Then you end up with a lot of hypotheses sometimes, anyway.
Right.
Now, on a galactic scale, what would MOND look like? In other words, what effect would it have on the interior motion of the Milky Way? In other words, would certain things align and be indicative that MOND is at play?
Can I take this one?
Yeah, go for it.
Okay. Yeah. So for the Milky Way, mostly what has been traditionally tested, and it's not just for the Milky Way, but for other galaxies as well that we measure. In fact, sometimes the Milky Way is the hardest galaxy to study, and we study external galaxies instead. It's mostly these rotation curves. So what you're looking at is in the plane of the galactic disk, how are the stars orbiting around the center. But the stars also bob up and down out of the galactic plane, and that's the vertical motion problem. And we have very little data on that, especially in other galaxies. And the exciting thing is that that type of data is now beginning to be available within the Milky Way. There's a ESA, European Space Agency mission called Gaia, which is doing an incredible job of measuring like literally 1 billion stars. It's measuring their positions and velocities. Unfortunately, not the acceleration, but just these two things. So quite a lot can be learned from this. So I guess what I'm saying is that we're now entering an era where we can test MOND within the Milky Way in new and stringent ways as well. We can test how stars move in the vertical dimension. Let me try to explain this idea because it's one that Kate and I stumbled upon. And I say stumbled upon, I mean, we discovered it, but then we found it was also known in the literature because, we were new to this field at the time. So the idea is that if you have a star, if you try to pull it out of the disk of the galaxy, the gravity of the rest of the stars in the galactic disk will tend to pull it back. And so it tends to snap back. And so they bob up and down because they get pulled back down. This happens in MOND, but it doesn't happen so much in dark matter because in dark matter, the galaxy is actually presumed to be essentially spherical. And so the plane of the galaxy, the disk that we actually see is just light froth. And really, most of the galaxy is supposed to be this spherical halo of dark matter. So if you lifted a star out of the disk of the Milky Way, it wouldn't tend to fall back down into the disk. So these vertical accelerations could be a very, very sharp test of MOND versus dark matter, and it's something we talk about quite a lot between us, and the community also does.
So the motions of the star, in other words, do we have enough data on the bobbing of the stars to say, well, maybe, or if we don't, how do we collect that data?
Yeah, so it's a little bit indirect. I mean, so Gaia is wonderful because it measures the position and velocity of all these stars. Absolutely. So this is quite remarkable because the oldest way to measure the distance to a star is parallax, which I don't know if you're familiar with that.
Feel free to explain for anybody in the audience.
Well, parallax is just something you can observe if you just hold up your finger in front of your face. And if you close one eye versus the other, you can see it shifts relative to the background. And the same thing happens that if you look at a nearby star against the background of more distant stars, and you do it today, and then 6 months later, when the Earth has moved to the other side of its orbit, these nearby stars shift a little bit. But the amount of things shifts depends on how far away it is, and the amount of these stars seem to shift is really tiny. People had conceived of this way of measuring stars like thousands of years ago, but it wasn't actually pulled off until the 1800s. And really, until most of the 20th century, this parallax method, it's absolutely unambiguous. You measure a distance with parallax and nobody can argue with you. There's no interpretation involved. It's just simple geometry and a simple observation. But it could only be done for a handful of stars until the early 20th century. And Gaia is able to do this for a billion stars and out to thousands of light years. So it's quite transformative. It can also measure the velocity, and I won't go into the gory details here, but it can measure the velocity of the stars also, absolutely. But what we really need is the accelerations in order to, the the acceleration, and then we want to break it down into components, into the vertical acceleration, which is, perpendicular to the plane of the galaxy, and the radial acceleration, which is towards galactic center. It doesn't do that, so we have to do some fitting and make some assumptions, some models of the galaxy in order to connect the velocities and positions to the accelerations. So some interpretation gets involved there. So people argue about it, and experts argue about it. A few months ago, there was a paper that claimed, based on Gaia data, that there was no dark matter in the Milky Way, but everybody else is highly skeptical that that analysis was right. So it's going to take a little while and a great deal of argumentation before we can build a good consensus acceleration model for the Milky Way based on Gaia data. And then we could test MOND.
I wanted to add a few more things that come to mind with what I thought your question was about. What would MOND say about the galaxy, the Milky Way galaxy? So a few things came to mind there. And I guess this is where MOND does a really good job of explaining observations, is on galactic scales. So to answer your question specifically, we would have to say which version of MOND we're using, and specifically what region of the Milky Way or other galaxy we're looking at, or we'd have to be a little bit more specific in order to answer your question in a detailed manner. But one of the things, or a couple things, that MOND generally is good at doing, I'll just say these without, I guess, acknowledging that this is where MOND does well. So the first thing is, the galactic rotation curves. MOND is able to explain the galactic rotation curves without invoking dark matter. And the way that the dark matter scenario explains those same rotation curves is something that Harsh mentioned. But in the standard cosmological paradigm, which is referred to as lambda CDM, lambda stands for dark energy, and that acronym CDM stands for cold dark matter. This is the standard cosmological paradigm. In that lambda CDM universe, the galactic rotation curves are explained essentially by embedding galaxies within these gigantic, essentially spherical halos of dark matter. So the fact that the luminous portion of that is the galaxy is just this little kind of blip, a luminous blip in an otherwise huge halo of dark matter. And it's that halo of dark matter that is the reason why the bobbing in and out of the plane is different in the MOND scenarios where there isn't any dark matter versus the dark matter scenarios where there is a bunch of dark matter. And that's actually not even what I wanted to clarify. But to me, that's the first thing that MOND would do, is explain the galactic rotation curves without invoking dark matter. But there's a couple of other wins, I think, that this, that MOND is able to do. And really, you'd have to talk to some true MOND supporters. I think if you talk to true MOND supporters, you'd probably find a few other things that they would like to mention here. And it might be worth clarifying that I don't think Harsh or myself is really like a card-carrying MOND supporter at this point, but we're open-minded about things. And if you're open-minded, I think you can admit that MOND is able to explain several galactic scale phenomena quite well. One is essentially the motions of galaxies in terms of what the MOND community calls the radial acceleration relation. So when we look at how galaxies are moving, and galaxies are vastly different from one another. There's all types of different galaxies, and one of the, I guess, wins, I call it, from a MOND win from approximately 2016, I believe, was the observation of, I think, a couple thousand galaxies with a wide range of morphologies and behaviors and so forth. And folks looked at how the acceleration of the luminous matter in the galaxy is correlated to essentially correlations between the acceleration in the galaxy and the amount of what's called baryonic matter, just ordinary luminous baryonic matter, not dark matter. The point is that you can explain how the galaxy is moving without invoking any dark matter. That's an observational statement that the galaxies appear to be moving in a way that doesn't require dark matter to explain them. So I think that MOND supporters would count that under something MOND is able to do, ways of looking at galaxy motions without invoking dark matter, not just the rotation curves, but also this radial acceleration relation. And then there's also another property called the baryonic Tully-Fisher relation, which again, I think if you are a MOND supporter, you file this under something MOND is able to do. But if you're in the dark matter camp, it's just kind of like, well, maybe not such a huge win. But I think those are a couple different ways in which MOND kind of addresses galactic scale physics, galactic scale observations in a manner that agrees with observations. The last thing I want to say points to our own work and the paper that we're talking about here, the Planet 9 paper. MOND predicts that these distant Kuiper Belt objects should be aligned. So this is not on the galactic scale, but this is, on a solar system scale. To me, this is something I take very seriously because I trust our work. There's a prediction that more of these Kuiper Belt objects that meet the stringent criteria that we've described in our paper, that they really ought to be aligned with the galactic center. So that's something that we're going to be looking for. Maybe not galactic scale predictions of MOND, but that's a prediction of MOND.
So I just wanted to summarize the situation with the galaxy, and I just say that both dark matter and MOND are able to explain the rotation of stars within the plane of the galaxy, but the bobbing up and down out of the plane, they would make drastically different predictions. And so it's very exciting to see if one could test that. But I think what Kate correctly pointed out is that even within this problem of just looking at the rotation within the galactic disk, MOND scores some really, telling points. And one of these is the baryonic Tully-Fisher relation. So I mentioned that the further out you go, instead of finding the speeds becoming slower, they flatten out and it becomes constant. All the stars are moving at the same speed. What the baryonic Tully-Fisher relation notices is that this speed that it levels off at, this constant speed that distant stars all pursue, is determined is correlated with the mass of the galaxy, with the visible stuff. And so in dark matter, the visible stuff is just like light froth, and it's really the dark matter that's supposed to be controlling the speeds of distant stars, not the visible matter. So it's a case of the tail wagging the dog, and that is indeed very surprising, as Kate was pointing out.
Now, Dr. Brown and Dr. Mathur, in regards to the solar system itself and your paper and the predictions that you're looking at MOND and what it predicts regarding these outer solar system objects and how they're aligned, go ahead and give us an overview of that. Dr. Brown, you start.
Yeah. Okay. So I'll try to keep it brief, and you tell me if this is like what you have in mind. But I guess the overview is the following: in Newtonian gravity, the solar system, and including the outer solar system and things like the Oort cloud, which is really quite gigantic, goes maybe even as far as like halfway to the nearest star. The Oort cloud could be really a large structure, but even structures like that, according to Newtonian gravity, would be all moving uniformly in the gravitational field of the galaxy. So the Milky Way galaxy, according to Newtonian gravity, should have no net effect on the motion of the objects in the solar system. Now, that is not true within MOND. Within MOND, there is something called the, quote, external field effect, or the EFE, which essentially gives the external field of the Milky Way. And again, I mean, it's I'm doing like air quotes here on external field because, of course, the solar system would be like embedded within the Milky Way. But within Newtonian gravity, the so-called external field that is due to the Milky Way would have no effect on the motion of objects in the solar system. Whereas in MOND, the external field of the Milky Way could affect, and what we found is that it would affect the motion of objects in the outer solar system. And so our model is very simple. We basically include only the sun and the galactic center. And so that's a very much an oversimplification. But what we find is that the presence of the galactic center would draw gravitationally these orbits into alignment with itself. So somewhere on the sky, there's a direction that points towards the center of the Milky Way galaxy. And what we found is that the very same 6 Kuiper Belt objects that have been used to motivate the Planet 9 hypothesis, their semimajor axes, when plotted against or superimposed on the direction towards the galactic center, they line up quite well. And this is like, I guess what I see as the overview is the dragging, the gravitational alignment, or dragging, I guess is what I'm referring to it as. The Milky Way galaxy would be dragging the orbits of these distant Kuiper belts into alignment with itself. So that's one, I think, a really neat idea, and two, a physically real idea. and I guess that's what I would say is the overview of the alignment according to our model.
Anything to add, Dr. Mathur?
Yeah, no, I think that was a very good explanation. So what I'll do is what scientists do, and I'll pepper it with footnotes and caveats. So one thing is that, yes, indeed, the galactic field has no effect in Newtonian physics, and it's very dramatic the way it does have an effect in MOND. And that's what we kept in our model. And I think that's actually a pretty good approximation to keep just the galactic field, which is and the field of the sun. And, it's almost inescapable that picks out a particular direction. So the orbits must respond to it in some way. And our analysis does show that they tend to line up. But then you could ask, how strong is the alignment effect? Like, are they absolutely forced to line up, or can they make, small angles? And how far can you go? What would be the distribution of angles? And some of those questions would require us to do additional work that we are trying to, we're actually working on right now, which is, everything we did was a kind of pencil and paper analysis. And it's very beautiful how far you can go with these wonderful techniques that were invented in the 18th and 19th century. And 18th and 19th century. But we'd love to get some computer simulations as well. And I can explain, if you're interested, why that's difficult and why it's going to take us a little while to get those going.
Absolutely.
Okay, yeah, I'll come back to that in just a moment about the challenges, because that's what we're working on a little bit right now. But I also wanted to add more caveats, which is, so you look at this alignment, you could say, wow, that must be because of a planet. Why else are these orbits aligned? Or you could say it could be MOND, but it could also be what's called observational bias. And so for this, let me just back up and explain what that idea is. We're talking about objects that are in what's called the extreme Kuiper Belt. So these things go really far out, and only a handful of them are known. All of them are in extremely elliptical orbits. And the reason for that is that if you had something that was in a circular orbit and was 500 astronomical units away, we wouldn't ever see it. We don't have telescopes that are good enough to see these small chunks of ice at 500 AU. The only ones we can see that go really far out, that go out to 500 or 1000 AU, are the ones that swoop in and come to 80, 100 AU, as some of these objects do, and then they swoop out again. So we always see them when they're at their nearest point. And so, the directions in which we see them, which is the directions of these major axes that Kate was pointing out, we're already seeing them in exactly those directions. So if you see those directions lined up, it could be just because we've only looked in a certain small subset of directions, and it's true we haven't done an all-sky survey. It could also be because those directions are easier to see because the skies are darker, because you're looking away from the galactic center. So those are the kinds of things that are considered observational biases. So I think what Kate and I believe is that we should wait for hundreds of these objects to be discovered. And that's another interesting question that I know you've already kind of indicated you'd like to talk about, what future discoveries are we waiting for? Yeah, so I guess those are some of the caveats and fine prints that we would love to do these simulations to test just how strong of an alignment, just how strong this alignment effect really is. And secondly, what's the situation with observational biases? Oh, actually, one more thing. So that's why I think Kate said this earlier too. That's why we're truly agnostics. I mean, I feel like there are three possibilities here: that there is no effect, it's just observational biases. But that would be interesting for us, because if MOND predicts an effect and it's not seen, then that is a challenge for MOND. Or it could be that Planet 9 is found tomorrow, and then of course, that's the explanation right there. Again, that's interesting for us too, because first of all, who wouldn't be excited to have a planet discovered? But it will also be, again, a challenge for MOND. So, we learn something about MOND either way. But obviously the most favorable situation for MOND would be if Planet 9 is not found and the alignment is, when hundreds of these new objects are discovered and the alignment persists. You can't say it's an observational bias anymore. Then that would be kind of evidence that maybe supports MOND. So
kind of a big deal.
Yeah, it would be kind of a big deal, right? Because it's not every day a new planet's found, but it's also not every day that a new law of gravity is discovered. I kind of enjoyed the title of your video earlier. It's sort of like, one of Oscar Wilde's things about the only thing worse than being gossiped about is not being gossiped about. And I guess the only thing better than finding a planet is not finding a planet.
Now, there's one other thing, Dr. Brown, I wanted to ask you about that you worked with, and it intrigued me because there has always been a question about the artwork of Jackson Pollock, a 20th century artist, that some people say he was using mathematical, I guess, calculations or something within his artwork. And there's been this sort of mythos about that. But it also led to a question of fakes. And there has been this sort of aura around his artwork regarding fakes for a long time. And I understand you did some work on that to see if any of that was true, if any of that mathematical stuff was real, and if that could be applied to identifying fake artwork. Tell us what you did.
Oh gosh. Yeah, so I love talking about this, and thank you for asking me about this. And this is referring to work that Harsh and I did back in 2006. For myself, it actually started a couple years prior to that. I was working on it alone as like a maybe second year graduate student, just sort of tinkering with these findings of some other researchers who claimed that Pollock was creating unwittingly fractal patterns in his paintings that arose from his motion around the canvas, which they supposed was chaotic. So there's like known links between chaotic motion and fractal patterns. And the idea that these researchers had set forward was that Pollock was moving chaotically around the canvas. And as a result, you could identify fractal patterns in his paintings. Not only could you identify them, but that they were unique to him, and that he was able to create the same fractal characteristics in layer after layer of painting after painting, so that by identifying those key fractal characteristics, they essentially form these unique fractal characteristics essentially form a mathematical signature that Pollock was unknowingly putting into his paintings. Now, that idea is very interesting to me. I thought it was an interesting idea as soon as I came across it. And I tried to discuss this work at a seminar where, like, as a graduate student, you're asked to give these talks. And I was all disgruntled about having to give a talk, and I hadn't really done any research yet that I thought was interesting enough to talk about. And so I came upon this fractals and Jackson Pollock business, and I thought it was really interesting. So I decided to just talk about that, even though it had nothing to do with cosmology, which is what the seminar was supposed to be on, particle astrophysics. But it was really interesting, and so I tried to fill in some of the details of this paper, which claimed that the fractal signature was not only there but also unique. And in the process of filling in some of the details, I discovered that the mathematical signature idea is completely false. The so-called fractal characteristics that they had assigned to Pollock's paintings were things that I could produce in a matter of seconds using Adobe Photoshop, no chaotic motion, just really scribbling on a digital canvas using a mouse in Adobe Photoshop. And that really surprised me, because I thought that this was a good idea. I really liked the idea that chaotic motion could leave these fractal trails in this, in these abstract paintings, which have this reputation for being kind of like, well, what am I looking at here? And is this art? Now, the idea that there was some mathematical content lurking in these drip patterns was exciting to me, because I can understand math, but I felt like I couldn't understand his art. So I thought it was a cool idea, but it turned out to be totally false. And this pertains to the authentication component, like with the fake paintings. Yeah, you can absolutely create the same fractal characteristics that had been previously attributed to Jackson Pollock, and only Jackson Pollock. You can do it, I can do it, pretty much anybody can do it, because they are not robust features of an image. They can be essentially generated at will, these fractal characteristics. And the core problem with this idea that Pollock was painting these fractal patterns is it comes down to the scale of the paintings and the number of orders of magnitude over which you can observe fractal behavior. And a Jackson Pollock painting, even though many of them are quite large, the most famous ones are quite large, the scale that you can access over which you can observe the fractal behavior is too small to reliably infer anything about the painting, and specifically anything about fractal content. That's why it's so easy to recreate those same so-called fractal signatures in any other image. It's because it's not really a robust property of the image. Does that answer your question?
It does. That's very interesting because, again, all of the controversy surrounding that.
Yeah.
Harsh?
Yes, I would like to, if I may, just offer my perspective on this also very briefly. So, as Kate says, she was a beginning graduate student when she did this work. And I must say, I was very impressed because the work she was critiquing had been published in Nature. So it's impressive when a beginning grad student isn't overawed by the prestige of Nature and is willing to tell you what they really think. And it's so, and the other thing is because it was largely her work, I can brag about it. So my favorite part of it was this childish drawing of stars that Kate drew that was in our paper. And we called it Untitled 5. And it is an authentic Pollock based on those fractal criteria. And this drawing not only wound up in Nature, but was in newspapers all around the world, and it's in a textbook as well. So it was really quite a, impressive piece of work for your startup project as a beginning grad student. So I suppose it's no coincidence that we are still working together 20 years later.
Absolutely wonderful. Well, thank you both for being here today. We are out of time, and I look forward to more Kuiper Belt objects and seeing just if they conform to this. It's going to be really interesting.
Yeah, thank you so much.
Yeah, it was fun. Thanks for inviting us.